the key to the hotspot, which formed the Hawaiian Islands, one of the U.S. states, was the fact that there is a fixed spot, a hot spot, a particular spot in which magma keeps coming up sporadically over time. And what it does is essentially just like a lava lamp. This lava comes up to the top, and eventually it breaches and comes into contact with the crust, and eventually creates a landform, creates an island, a bulge. Now, sometimes this island actually, stays underwater because it just doesn't get big enough. But you look at the new Hawaiian Islands, the newest is always the biggest, as it is being formed by this particular fixed spot that does not move. But on top of that, most certainly, that what does move are the plates. And so we already showcased that. And so what we have is a fixed spot below our surface that does not move, that's bubbling up, magma creating new landforms. But on top of that, the plates are moving. And so we have coming up through the mantle this particular substance, this magma that eventually breaches the surface and creates a landform. But like I said, plates, they do move. And so what happens is it essentially creates a chain of islands. And so a new island will be formed, but then as the plate moves on, the hot spot dies down, everything kind of goes away. And then a new one, then the hot spot picks up again, and then creates another island. And so we have these chains of islands that we can see very, very easily in a video that you can find here. So a great 2-minute video that explains hotspots. Just go either a Google search or go through YouTube. What is a volcanic hotspot? And it's parentheses educational. Super good video. Does much better way of showcasing how these suckers form. But that's good and all. We're more looking at rate of motion in this particular lab. And here we have the state of Hawaii. It's a digital elevation model, so you can see the undulation. You can see the newest island, the Hawaiian island, the island of Hawaii, I should say. On the bottom right-hand corner is the biggest. Well, that makes sense because it's just formed. Over time, the other ones, they were maybe that big as in their early beginnings, but over time they get worn down via erosion and weathering. And so over time, all of these chains of islands, they eventually, once they move away from the hot spot, they start to get smaller and smaller and smaller. And here I have an image I stole from the internet. From Google Images is another way to showcase how we have these chains of islands. And so the fixed spot, the hot spot, does not move, but on top of it the plate does. So essentially what it does is it creates these almost symmetrically parallel from each other chain of islands that we'll actually see are much bigger than even the Hawaiian Islands, which we can see here when we zoom out and look at the entire Pacific Ocean. So now the Hawaiian Islands are actually that bottom right-hand corner of this particular kind of L shape here. And so now we can see that this chain of islands is actually massive. Now what the thing is most of these are underwater, so you wouldn't see these. Are what they call seamounts. But essentially what's happening is this is one big massive plate, the Pacific Ocean plate, that's been moving over time, and it's moved right over this fixed location, this hot spot that's just to the south and east of the big island of Hawaii. So we can see now the oldest versus the youngest, and so of course what's ever most recent is going to be closest to the hot spot that formed it. The directions. Use the map and the following information to determine the rate of motion of the Pacific Plate over the Hawaiian hotspot. The hotspot is showcased as that white star just to the south and the east of the big island of Hawaii. So the hotspot, it doesn't move. But on top of it, the plate, the tectonic plate, does move. And so that's what we're trying to do, is looking at how fast that tectonic plate is moving based on it going over this one fixed location, this one spot that does not move, this hot spot which created the chain of islands of the Hawaiian Islands. Further, the volcano that formed the island of the Niihau is 4.89 million years old. 4.89 million years old. Rate is the distance traveled over a period of time. We know that miles per hour, for example. The distance traveled is equal to the distance from the present location of the hot spot, the white spot, to the island of Niihau. You can see Niihau in the upper left-hand corner, or to the north and west of the big island Hawaii and the hot spot. So we have to first off find the straight line distance from southeast Hawaii, the star, to Niihau. And we do that by using the scale. And so the scale is over here on the map. So essentially what I did was just put a yellow line. This yellow line showcases the distance from the hotspot to Nihao. And then what we can do is we can then take that scale and compare it to our yellow line. So what I've done here is to just put the yellow line down here, it's same distance, just put it down here closer to the scale, and you can do the same thing. So you can do this with a ruler, or you actually can just use it with the side of a piece of paper, just by taking the scale and then just seeing how far it goes along this yellow line. So we have the scale showcases this red line. So what I've done here is this is the first 200 kilometers, second 200 kilometers. Now we're up to 600 kilometers, and we can see that it's just past 600 kilometers as far as this yellow line. So let's go ahead and use 610 kilometers from our scale. And so this is a very simple exercise to showcase the distance utilizing a scale, a graphic scale. So what I'm going to do now is going to walk you through these particular questions. And so what I'm going to do is explain them, and then on the next slide I'll give you the answers. So if you just want to ignore me, go ahead and just go to the next slide. What we're going to do with the first question, start by measuring the straight line distance from southeast Hawaii to Nihao. Use the scale on the map. We've already done that, 610 kilometers. Next up, we're going to take that number, that distance, and we're going to divide from it the age of the island. And so the age of the island, as it says in the instructions, is 4.89 million years old. And so the distance, 610 kilometers, divided by the age, 4.89 million years ago, will then give you the answer that you should see there in the blank for the rate of plate movement is blank kilometers per 1 million years. The next question is going to ask you to convert your answers or your particular answer in that previous question to centimeters per year. So in the previous were centimeters per million years. Now it's just centimeters per 1 year, one individual year, not one grouping of a million years. And so to do this, we have to first off convert kilometers to centimeters. And so you're going to have to do the conversion, convert the kilometer reading that you got there in the previous question, convert it to centimeters, and then divide that result by 1 million. Because once again, we have to go from change their time from being per 1 million years to per 1 year. And so that's what we do there. Finally, that would then give us the answer for the bottom. The rate of Pacific plate movement is blank centimeters per year. And here are the answers. The next question is asking, using this rate, how far will the Pacific plate move in 50 years? So we found in the previous question that the Pacific plate's moving about 12 centimeters per year. So really not that much. I mean, 12 centimeters, my hand's bigger than 12 centimeters. So what we have is a very, 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 very small amount of movement over the course of a year. But when we think about that in terms of a million years, it's a big movement. But using this rate, if we can project out in the future how far is it going to move. So it's simply all we do is just take that previous number, 12.474 in this case, and multiply it times 50, and that is the result there of 623 centimeters. And so that's how far we can expect it to move in 50 years. In terms of the plate direction, now this is critical thinking. I'm not going to give you the answers here. But we kind of have an idea as far as where the oldest island is and where the newest island is, and that should be good as far as determining which direction this particular plate is moving. Now we take it one step farther by looking at a series of islands that are part of this massive chain that we've shown beforehand is much bigger than just those 5 Hawaiian islands that we've zoomed in earlier. And so we look at this entire chain. We can then look at these different islands, the distance they are from the hotspot, but also their age, which they can find out via carbon dating. They can then essentially now look at, well, has this rate changed? How is it slowing down? Is it moving this particular plate? And to do this, we can just do the same mechanisms we did beforehand, where we just take the distance and divide from it the time. So, for example, for the island of Suoko, it's 4,860 kilometers from the hotspot. We divide from that 65, because that's, once again, 65 million years ago, and we get a result somewhere in the 74.8, 75 kilometers per millions of years. Secondly, we do Coco. Coco's 3,758 kilometers from the hotspot, so it's closer. It's formed 48 million years ago, and that's a rate of 78.29 kilometers per millions of years. I'll go ahead and let you do the remaining three. So what you're going to then do to answer the question is you essentially take the 5 results. And so the first 2 results are here, 74.8. The second result, 78.29. So you're going to then to add the other 3 results together. So you're going to get the sum and then divide by 5 because there's 5 of them. And then that's the average rate. So the average rate. And so you should get something, when we look at kilometers per millions of years, you should get something right around 90 kilometers per millions of years. I'll let you go ahead and do the work. It might be just a little lower, but it should be somewhere near that. And so once again, we're going to then take that number that you get in that particular question, and convert it to centimeters per year using the same tools, the same mechanisms we did beforehand. Finally, at the end, you just kind of using deductive reasoning. What you do is you first off compare the result in this page on this particular question with the one on the previous page to kind of see as far as rate, because this is obviously looking at much older islands, islands that are much farther from the current Hawaiian hotspot. Or what you can do is also look at the individual changes from these islands in terms of their rates. So already we can see from Silco to Coco, it's gone faster. Went from 74.8 kilometers per millions of years to 78.29. So you can already see how that rate is also increasing. So use the data to support your response.